Okay, good afternoon and welcome to the Computer Security Seminar from Purdue University. Our speaker for this last week of the semester is Yelena Mirkovic from University of Delaware. Her topic is a practical IP spoofing defense through route-based filtering.
Thank you. Thank you for coming on such a cold day for the last seminar of the semester. I'm really honored that so many people came. I will talk to you today about defense against IP spoofing. It's called Clouseau, and Clouseau is really just a protocol that we use to build tables that are then used by route-based filtering to detect and filter out spoof traffic. And this is joint work between University of Delaware, Google, and UCLA. So this is the overview of my talk. I will just briefly remind you what IP spoofing is. I bet all of you know that, but I'll just go over that briefly. And then I'll talk a bit about route-based filtering, which is one defense that has been proposed against IP spoofing. And the way route-based filtering works is that we would have this notion of what is an expected path between any source and any destination. And then routers somewhere in the core of the internet would have tables denoting those paths between any possible source and any possible destination. And they would use this knowledge to detect packets coming on a path that is unexpected given their source address. And then those packets would be considered spoofed and filtered. There has been prior work in route-based filtering. Ki-Hong Park from Purdue actually did this work, and he looked at how effective this would be if you deployed it at a few points on the internet. And he came up with the result that if you deploy it at 18% of the all DASs in the internet, it would be very, very effective. It would be 98, 99% effective. We looked at a slightly different question because even 19% of all the ASs in the internet is a pretty large number. It's about 3,000, more than 3,000 ASs. So we wondered what would happen if you only had 5 points to deploy this on, or maybe 10 or 20, or at most 50. Could you be effective? And it turns out that you could be around 95% effective even if you had 50 points to deploy this on. We also looked at how complete should tables be. What if we have tables that are partially complete? And it turns out that if we have partially complete tables, our effectiveness goes sharply down. So what we really want is to have tables that are 100% complete. What this means is that we somehow have to find out proper information to build these tables. And when route change occurs, you see when the route change occurs, it will be a problem for us because our tables will tell one thing and the packets will be actually coming on a different path. So at this point, we have to infer that the route change has occurred and to update our tables. Clouseau protocol does that. So when we have unexpected packets coming on an interface that is not the proper interface for the source address, Clouseau protocol will kick in and it will basically do some decision making to figure out whether there has been a route change or whether these are spoofed packets. We will also set spoofed packet filters once we reach our decision and we are pretty sure that there is spoofing going on. We will start filtering packets that are offending. And Clouseau can act, it's pretty accurate in all our tests. And it acts pretty quickly, so within half of the second, we can reach a decision whether there was a route change or spoofing. So there are basically 3 parts of my talk. The first part is IP spoofing, and I'll go quickly over this. IP spoofing occurs when someone puts a fake source IP in the IP header and then sends the packet along. In this example, Andy, which has address 5678, is faking Leah's address 1234 in a packet going to Danny. So why is IP spoofing bad? Well, first, in my example, if Andy was sending malicious packets to Danny, such as, for instance, packets containing virus, then first, Andy would avoid liability by putting fake source address in the IP header. We wouldn't know where packets are coming from. And also, Andy could make Leah responsible for this traffic, because if we look at the source IP information, we would conclude that this was sent by Leah. So the attacker transfers liability to another person. The other misuse of IP spoofing is for reflector denial of service attacks. These attacks occur when the attacker sends a lot of requests, faking victim's address. For instance, DNS service request, the attacker sends them to a lot of servers, and then servers all reply back to the victim. And this traffic overwhelms the victim and invokes denial of service effect. When trying to deal with such attacks, it's not enough to just filter out offending traffic, because offending traffic is coming from legitimate servers, and it is legitimate traffic. So we would be effectively denying service to our users if we filter this traffic out. On the other hand, servers, they have no idea that these are bad requests, that these are fake requests. So they appear as legitimate requests to those servers. If we could handle spoofing, if we could reduce amount of spoofing, we would essentially handle reflector DDoS attacks. Spoofing is also misused in regular denial of service attacks when the attacker just sends a lot of traffic to the victim, and then spoofing really makes defenses hard, because if spoofing was not possible, what we would see when we collected statistics on the traffic coming into our network, being a victim's network, we would see a lot of legitimate users sending a little bit, and then we would see the attacker sending a whole lot, and then we would filter out this attack traffic. With IP spoofing, what we see is a lot of seemingly legitimate users sending a little bit, and we're still swamped, and we don't know what to filter. And so this is a common problem, not only with DDoS defenses, but a lot of other defenses for other security threats. They build profiles per user, and they try to distinguish who's a good user, who's a bad user, and user usually means an IP address, source IP address of the packets. So with IP spoofing, all those profiles are useless, because someone can either take over my profile or make me look bad by faking my IP address. So if IP spoofing were reduced, what we would get is we would simplify a lot of defenses. We would also get rid of reflector attacks or severely reduced reflector attacks. We would severely reduce the amount of damage from denial of service attacks, because if the attacker was randomly spoofing, only a small percentage of the attack would reach the victim, so that would be good. And the attacks would be easier to detect and attribute, because with limited spoofing, there would be only a few places we would go where to locate the attacker. So route-based filtering is one of the proposed defenses against IP spoofing. There are a few more, and I'm going to wait until the end of the talk. If there is time, I will give you overview of related work. If there's no time, then it's there on the slides, but then I'll skip it. Route-based filtering works by building tables that tell the filtering router what is the expected previous hop for every source address. So the router in this picture would remember that the top green rectangle is the expected hop for traffic coming from Andy, and then traffic coming from Leah should come on the bottom path. And then based on this table, we would do filtering, and we would be able to filter packets that come on unexpected path. The Kihong Park's work looked at the effectiveness of this filtering, and the reference is right there at the bottom. Route-based filtering should be very effective. There are some remaining problems, such as what should we do when the route changes, because then tables should change, and that's a big problem that we are addressing with Clouseau work. And then the other thing is that some spoofing will still be possible. Depending where you do filtering, you will detect some spoofed packets, but you will not detect all of them unless you do filtering everywhere in the internet. So here is the example of how route-based filtering would work. Let's say that my interfaces are numbered 1 and 2, and I'm remembering that traffic from Andy should come on interface 1 and traffic from Leah should come on interface 2. I will call this table incoming table. When Andy fakes a packet with Leah's address, this packet comes on interface 1, and then I would take the source address and I would do a table lookup, and I would see that the packet should actually be coming on interface 2. And based on this mismatch between the real interface and the expected interface, I would say this packet is spoofed, and I would filter it out. if at any point you have a question, feel free to interrupt me. You don't have to wait until the end. So you see that here I'm lucky because I'm doing filtering at this router that can distinguish between Andy's and Leah's path. And if I did my filtering instead on a router that is close to Danny, then paths from Andy and Leah would be the same, and I wouldn't be able to filter out spoof packets. So it really matters where I do my filtering, how much I'm able to filter. So Keegan Park's work said, yes?
Or not, but I just have a small question. On what system are you implementing this route-based filtering? Are you implementing on a router?
It would be on a router, and as I go through my talk, you will see that actually routers in the core that have a lot of neighbors, they are the best points to implement that.
Say, for example, that I spoof the IP address of a host machine, like this machine. Now, this machine is connected to a switch. Switch in turn is connected to the router. The router will store the address of the switch. So if you filter it on the router, but the source address, I mean, like I have spoofed the source address and not the IP address of the switch.
Yeah.
So then,
So I'm not sure I'm following your example, but I guess you're asking what happens with subnet spoofing, and subnet spoofing will not be distinguishable by route-based filtering. So you will be able, you within Purdue will be able to spoof other machines within Purdue. So I'm not saying we will eliminate spoofing, we will just reduce it. And that's our goal. We just want to reduce it to the level when you have an attack, a small portion of that attack reaches the victim. If random spoofing is involved. If the attacker is target spoofing, then he has some chance to find good addresses to spoof. Okay, so looking at route-based filtering effectiveness, Park's work showed that 18.9 deployment percentage gives us about 96% effectiveness. So 96% of source destination pairs cannot have spoofed traffic at all, which is really great result. And then 88% of ASs cannot spoof anyone, which is another great result. So this looks really good. It turns out that from this analysis, the best place to deploy route-based filtering is the vertex cover of the AS map. And Park's work tried to solve the problem of if I could deploy this anywhere, what is the minimum number of points where I should deploy it to have very, very strong guarantee that I'm handling spoofing. So this is really strong. I'm making sure that 96% of source destination pairs are completely free of spoof traffic. Vertex cover is a set of points where I should deploy that. And let me show you what the vertex cover is on a very small example. Let's say that I have this map. This is the map of the internet at AS level. It gets more complex than this, but in this example, let's just take this small piece. And I would like to pick nodes so that on every link, I have at least one node covering this link. I would like to pick minimum number of nodes so that I still cover all the links, but the number of nodes I picked is minimum. And you see why this is good, because then I have minimum number of deployment points. This is NP-complete problem, but a simple heuristic that should let me pick small vertex cover that is not really the minimum number, but it's close to minimum, works like this. So I'm going to first choose nodes that connect to the leaf nodes. And I hope you see that leaf nodes, they have those links that they have to cover. If I choose leaf nodes, I'm getting a lot of nodes in the vertex cover. If I choose the first neighbor of a leaf nodes, then I'm getting slightly less nodes in the vertex cover. And so that's going to be my strategy. I'm going to first choose those nodes that are neighbors of the leaf nodes. And then if any links are remaining, then I'm going to go try to choose the rest of the nodes in the vertex cover. So let me choose those that are connected to the leaves. And those are dark blue ones. And then I bolded the links that are covered now by those filters. So the remaining link is the one in the middle that is not covered. And I need to choose one of the nodes, either top or the bottom light blue one. So I'm going to choose the top. And so this would be my vertex cover. I have no guarantee that it's minimal, but it is vertex cover. It's covering all the links. Okay, so now you see that a lot of spoofing here cannot occur. So leaf nodes cannot spoof anyone because filtering is perfect for the leaf nodes. And then dark blue nodes, we are assuming that they are doing ingress filtering. So everyone who does route-based filtering also does ingress filtering. So there's no spoofing there. But there is still remaining spoofing on this picture. And if you look at the light blue node in the middle, it can spoof, let's say, going to the top light blue one, it can spoof this lower node, and it can spoof the blue node on the path. And that's because if you look at the paths between this light blue node in the, on the bottom and the one on the top, and if you look at the path between the middle blue one and the one on the top, you see that those paths overlap. And because they overlap, they're indistinguishable from the point of view of the filter that where traffic is hitting. So some spoofing will still remain, but a lot of it will be handled. So the main problem with vertex cover is that 18.9%, while this sounds good as a number, it's still a lot of nodes. Today we have around 21,000 ASs in the internet, and the number is constantly growing. So 18.9%, it's something more than 3,000 ASs, and these are 3,000 chosen ones. So this means I have to approach 3,000 different organizations and tell them, you should deploy this because this is really good, you know, and you're helping everyone else by deploying this. And chances are not everyone will do that. So the question that we would like to answer is, how well would route-based filtering work if I can only get like 10 organizations to deploy this? Do I have any benefit, or do I absolutely have to have a vertex cover? And then the other question is, what happens if incoming tables are incomplete? Do I still have good effectiveness? And if I don't, then how should I build incoming tables so that I guarantee that they are complete? Okay, so we'll now look at some effectiveness measures for route-based filtering, and I'll try to go slowly through this. There are a lot of graphs and a lot of measures here, but I'll try to go slowly, and then sometimes I'll just ask you to look intuitively at the area of the graph being reduced without really trying to understand what's on the x and y axis. We'll do this consideration looking at the AS map of the internet. So we'll purely look at this graph without any simulation. And looking at this graph, we'll look at all the paths from possible zombies. We'll let every machine on the internet be a zombie. So every zombie Z going to every other victim, every other address on the internet being a victim V, and spoofing the address S. Again, S can be any address on the internet. And so we'll look at those triples of Z, V, and S, and we'll see how the number of those triples that is possible is being reduced with filtering. We'll take into account different size of ASs. Park's work looked at every AS being equal. We will now look at bigger ASs being more important than smaller ASs. So we'll take the size into account, and all our consideration will be at the IP address level. We will evaluate filtering on AS map. I keep on talking about this AS map, and I should tell you how this is built. Route Views project is a publicly available database of BGP information from several BGP routers. And if you look at this information, there are there is ASPath portion of this information that you can use to build AS maps. So you can see how different autonomous systems on the internet connect to one another. And this is just a subset of the connections, so you cannot guarantee that you're seeing all the connections, but you're seeing a fair number of them. So you can use this information to build the connectivity map of the internet at the autonomous system level. There are some routing assumptions that we will use that mostly hold in the internet. The first assumption is that all hosts within an AS will follow the same path to a given destination. What this means is if I have one big AS, all the hosts going to, say, Amazon.com will take the same exit router out of this AS and go the same path. And this is mostly true. It's not true for very large ASs that are nationwide, have nationwide networks, because for them, there are different exit points depending geographically where the host is. Some exit routers are closer than others. And our analysis would work even if we didn't have this assumption, but it would be more complex. I would have more points there because I would have to break ASs into smaller networks. The second assumption is that the ASs advertise paths they take themselves. What this means is just a way that I have to guess routing. So once I have my AS map, I have to guess all the routes that all sources take to all the destinations. And I have some BGP information, so I have some paths, but I don't have all the paths. And what I can do is I can use shortest route guess, so I can infer shortest routes and say these are the true routes. And then to use BGP information, if I have a BGP AS path that goes 1, 2, 3, 4, what this really tells me is that AS1 goes over 2 and 3 to reach 4. If I have assumption 2, this also tells me that AS2 goes 3 to reach 4, and then AS3 reaches the 4 directly. And so that's mostly true in today's internet. The third assumption says there's a single path between two ASs. Again, if we had multiple paths, we could do the analysis, but it would be more complex, and I'm not showing that here. So how should I choose my filters? If I could choose any 5 or any 10 points in the internet, what would be the best points to choose? And the simplest way to grasp this is to think of the 3-dimensional space, think of a cube, and then 1 dimension are all the zombies in the internet. The other dimension are all the possible victims, and the 3rd dimension are all the sources that can be spoofed. So what I should do is for every possible filter, I should figure out how big a chunk of this cube is taken out because of my filtering. And then I should pick a filter that takes the biggest chunk out of this cube. And so let's say I'm picking the top one. I would do my analysis. I would see how many triples of zombie victim spoofed address are not possible because of this filter. And then I would say, I would do this for every possible filter. I would pick the top one that takes the biggest chunk amount of this cube. And then I would take this chunk physically out of the cube. So now the cube is smaller. And then I would repeat my analysis for another filter. And that would be the ideal way to pick top filters. Unfortunately, that takes a long time to compute. It takes several days to get first 2 or 3. So that wasn't the good way to go about choosing filters. And we came up with a heuristic that gives similar answer, that it's much faster to run. What we did is we, for every filter, we evaluated how good it would be filtering the portion out of this cube. And then we came up with a score that tells us how big a portion of a cube we filter. We would also then look at number of neighbors of this node and multiply this by the score that we got. So we would get a new score, including the number of neighbors in this picture. Based on this score, we would pick the top filter. And when we pick the top filter, we would take it out of the equation and we would repeat the game. It looks similar to what I told you before. What is different is that in the ideal choice of filters, in the top choice where I'm choosing optimal filters, I have to evaluate every candidate alone. So I have to let every candidate be the only filter on the internet, evaluate how good it does, then go to another candidate. And so that takes a long time. In the second approach, what I'm doing is I'm evaluating them all at once, and then picking the top one, removing it, and then evaluating them all at once again. And I'm getting pretty much similar choices. Intuitively, if you think what should be a good filter without going through all the analysis, think of all the nodes that have a lot of neighbors, they are good candidates because they have a lot of neighbors, which means that they can differentiate between a lot of paths. If I only have one neighbor, there's nothing to differentiate. I cannot filter anything because everything comes on this one path. If I have 1,000 neighbors, I have a lot of options to differentiate between. Also, if I'm on a popular route, I'm a good filter. That's because if I'm on a popular route, a lot of traffic goes through me, so chances are a lot of spoof traffic will go through me and I'll be able to drop it. If I'm not on a popular route, then I could do my filtering, but who cares because nothing ever goes through me. And so the combination of the popularity and number of neighbors makes a node good choice for filter. Okay, so we will now look at how different measures change when I take top N filters and I do route-based filtering on them. There are three measures that I'm giving you here, and the first one is something I'll call spoofability, and it's really just a number. It's averaged along all the three dimensions, the zombies, victim, and spoofed address. So it being an average, it doesn't tell you the whole picture. It tells you on the average how good the situation is, but it doesn't tell you whether it's good for everyone or it's good for selected few, and it's really bad for the rest. But it's a single number, and so single numbers are a nice thing to plot. So I'm giving you that one. It's a percentage of triplets that are still possible even though I'm doing filtering. So out of this cube, how big chunk is remaining with my filters in place? It's a number between 0 and 1 and 0. Numbers close to 0 are good. Zombie index is another measure, and it looks at all the possible addresses being zombies, and then for a given zombie, it looks at the average and the maximum number of spoofed packets that could reach any destination. So for the average, I'm going to average it over all destinations. For the maximum, I'm just going to pick the destination that is so unlucky that the zombie can send a lot of spoofed packets to it. And then I'm going to take this measure and I'm going to average it over all the zombies. So you see there's a lot of averaging going around. Intuitively, zombie index means if I picked my zombie randomly and I let it do random spoofing, and then I picked my destination randomly, this is how much traffic should reach this destination. Victim index is something similar to zombie index. So for victim index, I take every address to be a possible victim. And then I look at every other address being a zombie, spoofing randomly packets to this one. And I take the average and the maximum number of spoofed packets that would reach this victim from any given zombie. So for the average, I average it over all the zombies. And then I take this for all the victims and I average it over all the victims. So again, I get the number between 0 and 1. This shows you if I randomly picked a victim and then I randomly picked a set of zombies and let them send spoof traffic to this victim, how much would reach the victim? Again, on the average. So a lot of averaging going on. This is the figure that shows spoofability. The x-axis shows number of filters, and then the y-axis shows the spoofability between 0 and 1. And I'm showing you 5 lines for different years, so you can see how this changes over a year. Years are between 2001 and 2005, and then purple line is 2005, so that's the one in the middle. And then the light blue is for 2001. And so you can see first that the curve is exponential, which is always very good, which means that the first few nodes really have the big impact. So if you look at the first, say, 20 filters, if I have first 20 filters, spoofing really goes down. And then with 50 filters, spoofing goes down to about 5%, which means 95% of combinations are not possible anymore. You can also see that this trend changes over time. So in 2001, I had really good performance. Even with 20 filters, I could reach 5% of spoofability. And then in year 2005, I needed 50 filters for that. And so that's because internet grows. So I'm picking top players on the internet. As internet grows, top players become more numerous.
Do you have any kind of data which shows how much spoofing is going on because of the exclusive factory?
Mm-hmm.
They disable all sockets, so you can't spoof as much. And I think it's much easier to just generate sync packets or whatever without spoofing.
It is definitely easier to do without spoofing, and a lot of DDoS attacks don't use spoofing. But the thing is that some of them do, and then also when a lot of network telescope projects, they are tracking spoofing. So my guess is they would have better idea than I do how prevalent is spoofing on the internet. What I'm trying to address is, as long as it's possible to do spoofing at the large scale, we're not safe. Even though if people are not doing it today, it's very easy to do it. So, you know, if we don't take it out as a threat, it's still going to be there. It's still going to plague our defense system, so we won't be able to rely on our profiles and to do defense. Okay, this shows the zombie index. Again, zombie index is something that tells you if you picked a random zombie and you picked a random victim, how much traffic would reach this victim. And this is the average case in solid lines, and the dotted lines show the maximum case, the worst case for this measure. And you see that the worst case really doesn't look very good. So we're still around 80%. But the average case looks good, and so we go down to 5%. This shows that for some zombies and for some victims, spoofing still will be possible. But for majority of zombie victim combinations on the internet, we will cut down spoofing. And then victim index looks similar. So victim index tells me for the average victim how much spoof traffic should this victim receive on the average and at the maximum. And so you see that at the maximum with 50 filters, average victim should have its spoof traffic cut down in half. So if someone is doing an attack, then the worst case is that 50% of traffic would reach me as the victim. But the average case is that about 5% would reach me. Okay, so now averages don't really tell the whole story. And I'm hoping I'm going to have time to show you all the graphs that I want to show you. Averages don't tell the whole story because, let's say, a 10% zombie index, this doesn't tell me if this means that everyone can only spoof 10%, or if it means that 80% of nodes can spoof 0.1%, but then 20% of nodes can spoof 50% of addresses, which would mean that I have 20% of nodes that are really good choice for zombies, and then the rest is not a good choice. And we would want to look at this issue of how balanced are those measures over all the victims and all the possible addresses you could spoof. Whether if I have 50 filters, whether I'm helping everyone equally, or whether there is a chosen few that I'm helping and then the rest are just unlucky. And so ideally, we would want to have defense that is fair to everyone. So we'll now look at those measures. I'm going to show you a measure for each IP address. And then if this address is a victim, then I'm going to divide zombies into categories based on how much they can spoof to this victim. And if it is a spoofed source, if this is source whose address is misused in reflector attacks, then I'm going to show you for every zombie how many destinations can be reached if this address is spoofed. And if you think of reflector attack, it is only successful if I can spoof a given address to a lot of destinations, because a lot of destinations will then reply to the victim. So if I cut down on spoofing and my packets cannot reach a lot of destinations, then I'm not going to be successful with this reflector attack. Okay, so I know that there is a a lot of information here. And so what I'm going to do is I'm going to explain one graph, but then I'm also going to ask you to look at the color only. I'm showing you graphs for 1, 5, 20, and 50 filters. And so let me zoom in on one filter. And this is the victim measure. So on the x-axis, you see all the victims in the internet. So every point on this line is one victim. And I just sorted them so that I get a nice graph. I don't get graph all over the place. The color means level of spoofing. So the red color means in this area, zombies can spoof more than 10% of the internet, which I would call almost unlimited spoofing. You can spoof almost everything you choose. In the light blue area, you can only spoof between 1 and 10% of the whole internet. In the violet blue area, you can only spoof between 0.1 and 1%. And the dark blue is the best, because in the dark blue area, that's the best protection. Zombies there can only spoof less than 0.1% of the internet. And so what I would like, the y-axis shows the percentage of zombies that fall into these areas. And what we would like to see is first less red on the graph. So ideally, we would like to see the graph being dark blue. But if it cannot be dark blue, then at least blue, so that red goes away. And then the second thing we would like to see is graph being level. So for all the, again, x-axis are all the victims. We would like every victim to receive same protection. Okay, so let's look at the yellow line, and this is just one victim I have picked out. And this victim is ranked about 20 percentile in this case. And I did the ranking based on the level of red. So victims on the left are victims with best protection, and the victims on the right are victims for which we are not really doing much. So this one is somewhere close to the ones where we are doing a lot of work for. And for this victim, if you look at the y-axis, there are about 5% of zombies whose spoofing is severely reduced. And then there are about 10% of zombies that can only spoof 1% or less of the whole internet. There are about 30% of them they can spoof 10% or less, and then the rest, 70% of zombies, they can spoof anything. So this means that if this address was chosen as a victim, and I chose my zombies randomly on the internet, I would have a good chance of actually creating an attack on this victim. I'm not doing very good work protecting this victim. You can also see that here on the left, on the far left, there are a chosen few that are really having good protection. And for those chosen few, you see that they have almost all blue, which means that they are really well protected. If they are victims, they will only receive 10% or less of the spoof traffic going towards them. And so we would like these measures to level out, and we would like the red to go away. And so now, hopefully, you can follow those graphs without really bothering about x and y axis, just looking at how red they are and how level they are. And so you see that they start to level out as I get more filters. So with 5, it's kind of better, but I still have those chosen few, although chosen few is about 20% of the whole internet. With 20, it's even better. With 50, it's almost level. So with 50, almost all the red goes away, and the graphs are level, and I'm doing really good work for everyone. Okay, since we're running out of time, let me quickly go to another set of graphs. And they have similar meaning, except x-axis shows a source that is misused for reflector attack. So again, the meaning of colors is the same. So red is bad, dark blue is the best. We would want everything to be dark blue or at least blue. We would like red to go away, and we would like graphs to be level. And you can see that first they are almost all level, which is good. And then when I have 50 filters, then the protection for the reflector source is good all over the internet. So if I have 50 filters for a chosen source, let's say this source right here indicated in yellow, if someone wanted to spoof this source address, then about 40% of zombies, if they spoofed this address, they couldn't reach more than 0.1% of the destinations. And then half of the zombies couldn't reach more than 1% of the destinations. So it's pretty useless for the attacker to spoof this address because he's not going to end up having very strong reflector attack. Most of the destinations will not be reachable. Okay, so to summarize the effectiveness, if I have 50 filters, I'm doing really well. And then about 20 filters, first 20 have a considerable impact, and the rest 30 just help me level out this graph. I'm going to skip this part talking about filter membership because we're running out of time. I would just like to tell you that those filters tend to stay around. So if I choose my filters today, about 60% of them will still be around 3 years from now. They will be in top 50. So that's good news. And then some of the big players are long-term members. Long-term members are those that are in top 50 over 5 years. And so if you look at top players, there are 17 ASs, but there are only 12 ISPs owning these 17 ASs. You see that all the big players are there: AT&T, Sprint, Quest, UUNet. And then first 10, top 10 are US providers. And then the 11th one is European provider, and the 12th is Asia Pacific provider. So if I got those 12 organizations to deploy filtering, then things would look very good for everyone. Okay, let me skip the spoofability with partial tables because I would like to tell you how we actually guess those tables. We looked at how well the effectiveness would be with partial tables, and we concluded that it wouldn't really work very well, so we have to have complete tables. And then there are a couple of ways we could build incoming tables. We could ask people to send us reports, but then since not everyone would send us reports, we would end up having incomplete tables. Or we could try to guess the content of the tables, and we could do educated guessing. And so that's what Clouseau does. So the way Clouseau works is that when packets start arriving on unexpected interface, we start something called inference process. And out of the first n packets that come on this unexpected interface, we randomly choose D and we drop them. And we will only do that for TCP data packets because we expect those packets to be repeated by TCP. So we'll drop those D, and the rest we will pass, but we will remember them. So we'll remember the dropped one, we will remember the past ones, and we remember them so that we could identify them if they occur again. If those packets that we dropped have been repeated, then we will gather route changed points. And if packets that we let go are repeated, we will gather spoofed points. And so when we gather enough, let's say, route changed points, more than a threshold, then we will say there has been a route change, and we will switch our interface. If we gather a lot of spoofed points, then we will say there has been spoofing attack, and we will forbid the inference process for a while. So once we reach the decision, we ban the inference for a while. Decision is made when we collect either D route changed points or P spoofed points. So D and P are my thresholds for the decision. This illustrates how Clouseau would work. Let's say that I have chosen to drop the first packet and then forward packets 2 and 3. So the first packet is dropped and placed in the dropped queue. The second packet is forwarded and placed in the forward queue. And then the third packet is forwarded and placed in the forward queue. now let's say that the first packet is repeated. If it's repeated, I'm going to mark it as repeated, and I'm going to get 1 route changed point for that. Let's say that it's repeated again. So, let's say that packet 2 is repeated. So if packet 2 is repeated, I'm going to mark it, and I'm going to get 1 spoofed point. So let's say that packet 1 is repeated again. If it's repeated again, I don't get any more route changed points. So I only can get 1 point for 1 drop packet being repeated, and then I don't get them again. However, if packet 2 is repeated again, I'm going to get another spoofed point. And so that helps me to catch the attacker that blindly repeats packets. Okay, so
What if 2 is dropped by a similar route?
that's a good question. I'm just going to talk about that now. So the question you're asking, should P be greater than 0? Should I let some packets that I have forwarded be repeated because maybe someone else down the line dropped them? And the answer is yes. There could be congestion. Packets could be dropped down the line. So I'm going to let a few of them be repeated, but not too many. And then P is the threshold that I will set so that I make sure that for legitimate traffic this looks good, but the attackers have hard time to trick the protocol. Why do I have forwarded queue at all? Because if I didn't have forwarded queue, an attacker who just repeats every packet could fool me. And I would believe that all the packets, or all drop packets are repeated, and that's okay to change the interface. I also have a margin. So not all dropped packets have to be repeated. D of them have to be repeated, but my queue is actually D plus some margin. And the reason why I have this margin is because the application might die and some packets would not be repeated. So the margin is there just to be safe, that I'm not waiting for one last packet that will never be repeated. I will also time out if I cannot reach my decision. If I cannot gather enough points within certain time, then I'm going to say, well, you know, this is leading nowhere, and I have to time out. And if I time out, I'm going to conclude that spoofing is going on. In case of random spoofing attack, that's what's going to happen. So nothing will be repeated. I'm always going to get new packets, but I'm going to time out and figure out that this is spoofing attack. Once I reach my decision, I'm going to place a ban on inference protocol for a while. And the reason why I'm doing that is that inference mainly lets packets through, and I want to filter packets. So once I reach my decision, I'm going to filter for a while, and I'm not going to try to guess again for a while. Okay, I'm going to show you some performance measures. We tested Clouseau by implementing it in a Linux router and testing it in EmuLab network. We started 50 parallel legitimate connections between those 2 yellow nodes, and then Clouseau is implemented at this node that has Inspector Clouseau pictured above it. We have the routing going one way, and then in the middle of this transfer, we change the routing, so we go another way. And we are looking what impact does this have on legitimate traffic, and what impact does this have on the decision process? How quickly can we decide? This shows how traffic delay changes with queue size. The x-axis shows the queue size. It only shows the dropped queue because there is a constant relation that I'm enforcing here between dropped and forwarded queue. So dropped queue is 9 times smaller than the forwarded queue. And I'm keeping this ratio, so I'm increasing effectively both queues. The y-axis shows the connection duration. The blue line is the baseline, and the red line is the case with Clouseau. And so you can see that Clouseau doesn't impose large delay. It's basically less than a second delay in the connection. And it pretty much doesn't change with the size of the queues. This shows the inference time versus queue size. How long does it take me to reach my decision? And again, I'm showing you the same x-axis as on the previous graph, and the y-axis is the inference time. And you can see that the dependence is linear. Longer the queues, longer it takes me to reach my decision. I go from less than 0.05 of a second to about half of a second for big Qs. Let me skip the dependence of on the drop probability. There is also a dependence of like how big is the dropped Q overall when compared with the forwarded Q, but I'll skip that except to tell you that the dependence looks similar to when I increase the size of the Qs. I'm going to talk to you briefly about attacks. One possible attack is to repeat every packet. And it turns out that if the attacker wants to repeat every packet, the best number of repetition is 2. Because if I send one packet and then repeat it again, if the first one was dropped, I can get 1 good point, 1 route change point. If the first one was passed, then I can get 1 spoofed point. If I repeat packet more than once, then I'm going to get more spoofed points in the case that is bad for me when the first packet was forwarded. I'm not going to get more route change points. So to minimize the damage and to maximize the gain, the best number of repetitions is 1. So sending the original packet and repeating it once. Related attack that is actually identical to the previous one, but with packets repeated in different order, is permutation attack. So permutation attack means the attacker sends a sequence of n packets and then repeats a random permutation of this sequence. How likely is he to get the right sequence so that I change my routing and I believe that there was a routing change, that the spoofing is not going on? And so by looking at the permutation attack, I'm also looking at the packet repeating attack because those are the two same things, just shifted in time. The formula here tells you the probability that the attacker manages to cheat me. And instead of looking at the formula, let me show you the graph. So this graph shows you the probability of the attacker cheating me versus Q size. It's a logarithmic graph, so the y-axis is the log of the probability of the attacker cheating me. And the x-axis is the Q size. Oh, I'm only showing you the dropped Q, and the forwarded Q is 9 times that. And so you can see that the probability drops exponentially with the Q size. And if I have a Q size of 1,000, then the probability of the attacker cheating me is 10 to the minus 50, which is a really low probability. Okay, well, I think, am I out of time? Pretty much I am. Okay, well, let me then go to the questions. I have more things to tell you, but I'm going to skip that. So let me take a few questions.
We could probably take a minute or so, but then we'll have a class coming in. We can
Okay.
move out in the hallway if we need to. But are there any questions here?
Well, thanks.
Okay.
I'm sorry we ran out of time.
Thank you.